Hey guys, welcome to the recitation number 7. We're still in abstract algebra, and today I'm going to solve some problems based on the things we discussed in the lecture. But also I'd like to cover a bit about rings and fields. Maybe I'll show you 2 examples there. All right, so let's get started. I will start with something, an easy problem, which was basically you just have to use again binary operations. So the first problem that I have in mind is the following. So problem 1, and this was a Putnam B1 in 1971, so some time ago. Can you hear me well? All right. All right, so the problem states the following. Let me consider S be a set. And this time we'll define and let circ, so I'll define it in this way, be a binary operation on S, satisfying the two laws. And the laws are given by the following. So the first one is x circ x. If you don't like this circ, you can put whatever you want. It's x, but I'm just going to write the problems as it was stated in the on the exam for all x in S. And the second law is some kind of associativity, but not quite like that. So it's something like x circ y and everything circ z. And like I said, it's not quite associativity because is y, so this will be equal to y circ z circ x for all x, y, z, and s. And I'll explain immediately why this is not quite the associativity, because we have to show that. Show that this binary operation is associative and it's even more commutative. Okay, I want you to look at the problem a bit for a minute or two. Maybe you can come up with some ideas. So it's a very similar problem in nature with the one that we did before, right? We've done one in the lecture. So if you look at the second law, it's almost like associativity, almost. So if we swap those two, x and y, z, it was associativity. So that's what you have to do. Hey, Jack.
Hi.
So you know, the problem, the way it's stated, it's showed that this is associative and commutative, but you know, you don't have to solve it in the order that it is stated. You don't have to be like, oh my God, let me prove associativity first and then I will dwell on commutativity. Maybe you can do the other way around. Maybe it's easier to prove that this binary operation is commutative and then you show it's associative. Maybe.
Just to clarify, so binary operation would just be like the sum of two x's or two elements in S?
Not the sum is that operation. So binary operation, this means that this exists. For any two elements in the set, you can take the operation between them.
Or it could be any operation?
Any operation. It's a circ operation. It's not addition, it's not multiplication. It's this operation that is defined by only these two laws.
Okay.
So this is what you can do. If you don't like, you know, if you don't like circ, imagine that you have a dot there or plus, if you want.
But it's just symbolic of some operation, right? We don't know.
Yeah. It's just an operation that satisfies these two laws. So for this operation, if you want to replace it, x plus x will be x. It's not going to be like, so 2x will be x, or if you want.
So for the first one, is it the identity operation where you get back the same element when you do some operation to two elements?
Who did I tell you that actually identity exists here? You don't know.
Yeah, okay.
Did I tell you that? It's just a binary operation. We've said this.
For the first law, I was looking at it, and you get x.
It's kind of like an x squared if you want, or 2x equals x.
Okay.
So for example, if I start, so we want to use the given laws, right? So using so what do we have? Look, let me start with this. Let me start with commutativity. So it's x circ y. All right, maybe I should somehow apply these two laws in such a way so that I will obtain that x circ y is y circ x. So that's my plan. So what should I do? Well, using the first law, look at it. I can write this as x circ y circ x circ y, right? Instead of element x, I take x circ y, because what you know, since I know that this is a binary operation, you know that x circ y and y circ x exist, right? And it will satisfy those two laws. That's it. That's the operation. You cannot do anything else. You have to play around with this. And now, this is the trick here. Using the second one, in fact, this is the most tricky part of this. You can do it in the following way. You can somehow you would like to distribute this, but look at the second one. So I will have the following. It's x circ y, circ x, and everything will be circ y. Imagine the way we're going to do this. Okay, I'm going to tell you so that if you don't want to. So imagine this is a. Or okay, let me tell you how I will think of this. So imagine we have something like this. The order will be A, B, C, right? And A, B will stick together. Let me put them a dot between them. This is how I thought of it. And then I'll have here B, C together and A. So that's the order. So once you have A, B together, C will be B, C, A. Always keep this in mind, the way you're going to put the order. So you see here, if you look at this, right, the second one, just look at this guy. If you apply the second law, right, look at the guy here. So you will have that this is, let's say this is in this order, A, B, C, right? Or no, let me put it like this. No. I would, oh, okay. So we have X, Y here. And the way we're going to do it in the following, so that you can see it. Okay, let me, all right. Now, what we're going to do is just look at this guy. This, let's say this is an A, B, C, right? So A, B, C is B, C, A. So it's A, so it's B, C, A. So it's X times you see, it will give you exactly this. So it will give you X circ Y, circ X, circ Y, right? Okay. That was a tricky part, right? But now what I'm going to do, if I want to apply again operation 2, but I want to do it here inside. So once we do this inside, so again, I want to apply 2. And once we do this inside, what are we going to get? So keep in mind, X, Y. So in this time, this will be, the Z will be X. So it will give us what? So it will give us Y circ X, circ X, circ Y. Right? Okay, let me. So I only applied inside the operation, inside the parentheses here, I applied 2. Okay. Right? And now let's do it again. So this will be, again, I will apply 2. So this will be X circ X, circ Y, everything circ Y. So again, I apply 2 here, but now I will apply 1. I know that X circ X is X. So this will be X circ Y, and now by applying 2 again, right, this time I will apply 2 directly. It's this would be Y circ Y, right, circ X. And now applying I again, Y circ Y is Y, so this will be equal with Y circ X. So look where we started from, and look what we ended. So this means that this binary operation is commutative. Thus, is commutative. All right. So we have commutativity, but now we have to show associativity, and this associativity is for the associativity law. We obtain, let's see. So we start with X circ Y, everything circ Z. And now we want to apply 2 because you see the condition, the 2I is almost like an associativity. So this would be, if we apply 2, this will be, so X, Y, Z will be Y circ Z circ X, right? But now I will apply commutativity here. And this will give me X, so I know that these two commute, so it's X circ Y circ Z. And basically we're done. That's it, that's associativity. And we are done. That's the problem. That's it. Was it hard? So Jack, did you do it while we're discussing it?
Yeah.
Okay, wow, great. So these kind of problems are just manipulations of the two operations. You have to be well, you have to be inspired, but also to be able to manipulate them. Yeah. All right, so that's the first problem. As you can see, there were some similar problems in the 2000s with this one. Now the second one that I have in mind, so problem 2, this was a Putnam A4, 1994. And you will see it will be a similar problem in nature. And it says the following. Let me state it first. Let G be a group. And this time, Aaron, since you asked about the identity, well, I say this is a group with identity E. And we'll consider this map, then let's say phi from G to G is a function, so this is a function such that has the following properties. So when we have phi of G1 times phi of G2, phi of G3, this is nothing else than just phi of H1, phi of H2, phi of H3. Right? We have this property whenever G1, G2, G3 is the same as H1, H2, H3, and their product, whatever. So we say that this group is endowed with the dot operation, whatever, is the identity. Prove that there exists an element A in G such that this map here, psi of x, which is A times phi of x, is a homomorphism. And I'll explain immediately what this is. Those of you who have taken abstract algebra, you already know what it is. A homomorphism is something like this. So definition. Phi is a homomorphism. Let me just say phi from G to G. Psi, sorry, from G to G is a homomorphism. If psi of xy is psi of x times psi of y for all xy for any two elements in G. So that's a homomorphism. All right, so this is the statement of the problem. Look at it for a bit. Keep in mind that we're dealing with a group here. So when we're dealing with a group, you will assume all the properties of the group. So let me say that. This is a group with identity. And we have a map that satisfies that property. So you have to show that there exists this map, A times phi of x is a homomorphism. So there is one thing about homomorphisms. So what do you think is going to happen to homomorphisms if you look at them? With respect to the identity, can you tell me? So they will send the identity into what? So homomorphisms send the identity E to E, to the identity. That's what they do, right? It's quite clear to see this, right? Because if you take X and Y to be equal to the identity, right? Just take this, and it will follow that psi of E times E is psi of E times psi of E. But this is nothing else than just so it follows that psi of E is E. Right? Okay. So at this point, we know that psi of E is, so E squared is E, so no problem, no problem. I know that, so we can take let's take A to be, let's say, psi inverse of E, right? And now we have the following. Clearly, the map psi of X, right? Defined in this way, phi of E, phi inverse of E times phi of X satisfies this here. So that satisfies psi of E is E. So it sends the identity to the identity. So now we have to show that this is a homomorphism in this way. Now, let's see, what can we do here? So look at this relation here. So we have to play with it. We have to play with this. But also, this doesn't just hold true for any 6 elements, G1, G2, G3, and H1, H2, H3. Moreover, you see, when I dot them in this order, it will give me the identity. So we have to play around with this somehow. So let's see. First, what should we see? First, let's note that phi of G, and now I'm going to do the following. Times I'm going to take one of the elements to be the identity and the other one to be the inverse, right? So I know it's a group, and I know that you see G dot E dot G inverse, it will be the E. This is nothing else than just phi of E times phi of G times phi of G inverse for all G in G. All right, so we have this, right? This holds true because it, right? Okay, let me just say here that G, E, G inverse is the same as E, G, G inverse, right? And it's E. So any elements you pick, this holds true. So that's why you think of to pick some of the inverses. You know the inverse exists because it's a group. You have the identity. So maybe you should play around with this. So from here, if you look at it, you know that what does it follow? It follows that it follows what? that phi of G times phi of E is, so now you can cancel these phi of so this guy. You see, it's the same as here. So that's the trick. So we can get rid of it. It's the same as phi of E times phi of G for all G in G. All right, that's a good relation that we have here. Let's keep this in mind. So we have this one thing. Okay. But now we can do some other things as well. So again, it's a very similar in nature with the first problem. Well, it's a little bit more involved because you have this map, so you have to show a bunch of things, but it's basically the same. What else can we do here? If we look at it. So does this imply that, well, if we multiply by, so if we multiply by phi of E inverse to the left, to the right, it will follow that. So this also, ooch, this implies that phi of E inverse, right, commutes with anything in the image of phi. In the image of phi, right? I hope this is clear for everybody. Just look at this relation, multiply by phi inverse to the left, right? It will go away, and then you multiply by phi inverse to the right. I'll leave it to you as an exercise, but I just told you what to do. Okay. Now I'm going to do the following. I'm going to play a bit. Now, next, let's observe that. And the way I'm going to play is in the, I'll do it in the following way. So if I take, let's say, phi of x, if I take elements now, phi of x and y, phi of y, and now the last one is phi of y inverse x inverse, right? This will be phi of E times phi of xy times phi of y inverse x inverse for all x, y, z in G. Why is that? Let's see. Again, if you look at this, look at these elements, x, y, x inverse, y inverse, this will give me E, right? And if we look at these elements, E, x, y, y inverse, x inverse, again, they will give me E. You see? So I can play around, I can arrange elements in such way, their product, whatever, they dotting them, it will give me the identity, because that's the condition here, you see? So anyway you pick G1, G2, G3, when you dot them in this order, they will give you the identity, they're equal. So that's what you're going to do. So this is what so imagine that this is like a G1, this is like a G2, this is like a G3, and this is like a H1, this is like an H2, and this is like an H3. See, when you dot them, it will give me the identity. So that's how we're gonna play. But now if you look at it, so, but I'm playing in this way especially because I want to get rid of this guy. You see, they're the same. So we can cancel this. So now we can cancel phi of y inverse x inverse, right? And once we cancel this and we obtain So what do we obtain when we cancel this? Can you tell me? So we'll obtain what? Phi of x, phi of y is the same as phi of e times phi of xy. Are we close? Well, almost there. Let's keep this relation in mind. We're almost there. But what can we do to what would you do here? Keep in mind that you have to obtain something about this psi of x is. We said that a is. Yeah, we said that a is this guy here. Is phi of e inverse, right? And let's say squared. Maybe something like this is phi of x. Wait, yeah, what is it? Wait. No, it's phi of x. So keep in mind that is this. We have to obtain a relation about this guy. So maybe I should do something to this equality. Let's call this a star. So what should I do? Well, maybe I can multiply by something, but so multiply star by what? Well, I have this element here. So maybe I should play around with it a bit. So I can multiply this by phi of e inverse squared. And we have the following. And you'll see why I'm applying. Well, you know that phi of, and okay, let me mention this again. And keep in mind that what? That phi of E inverse commutes with all elements in the above equality. Commutes with all elements in the above equality in star. All right, so once we do this, so we obtain the following. So finally, we obtain that what? That if we multiply by this, so we can redistribute, right? I'm multiplying twice by it because it's squared. So I'm redistributing it. So I'll have phi of E inverse phi of x, phi of E inverse phi of y, right? Is the same as, so it's phi of E inverse phi of xy. And this happens for all x, y, and g. Okay, so we have this. Well, are we done? Who is this guy? It's psi of x. Who is this guy? Psi of y. Who is this guy? Psi of xy. Isn't it what we wanted to prove? So this is, so psi of x, which is given by this guy, and you can call this an element I, A times phi of x is indeed a homomorphism. And we're done. That's it. You see, that was the problem. So basically just playing around with elements and rearranging them in a smart way, I would say. but you don't have too many choices. When you have three elements in the group and you dot them, all three are together, and it gives you the identity, you would think that you should play around with some of them should be identity, with some of them should be the inverses of the others, and you put them in such way so you can cancel as many as possible, right? That was the main idea. Was it hard? Jack, what do you think about the problem?
I thought it was pretty easy once you figured out what A should be.
What A should be, right? Yeah. In fact, that's the most tricky part, I agree. Anyway, so these are more computational. Let me give you something a little bit more conceptual. And this is a problem on the list, on the worksheet, which says the following. It's pretty classical, I would say. And it says that if I have a G, a group, and I put here the dot, so this is a group with 10 elements. You see, not too many. A finite group with 10 elements. In which, in fact, we have a property in which there exist elements A, B, in G, but these cannot be the identity such that A squared is the same as B squared and is the identity. Show that G is not an abelian group. So you see, remember we had this problem in lecture when we showed that if you have a group and if x squared is the identity for all x, then the G is abelian. Now I'm providing you a group with 10 elements for which there exist 2 elements which are different from the identity such that the square of those elements is the identity. So G is not an abelian group. So for G to be an abelian group, all of them must satisfy this property for any element in it. So show that this is not an abelian group. So it's kind of correlated with that problem, related to that. So think about it for a bit. So how would you approach this problem? Well, it's clear that maybe you don't have too many conditions here, but if you want to get an extra condition, what you should do? Maybe assume by contradiction that G is abelian. So when I say abelian, this is commutative. So any 2 elements you pick, they commute. All right? So this implies that, I want you to look very carefully here. So this implies that if I take 2 elements, let's say A, B, and I know that A and B are not the identity, so this will be different. First of all, will not belong to this set, the identity, right? What else? It cannot be A, because otherwise B will be the identity. It cannot be B, otherwise A will be the identity. We know that. So in this way, we can form a subgroup, right? So we have this H with, let's say, with these elements, A, E, A, B, right? So this is a subgroup of G, right? That's obvious, I hope. But what do we know from the Lagrange's theorem? How many elements does this subgroup have? Wait.
Is that a subgroup?
No, actually, let me. A, B, and AB. Now it's more like it. Okay, let me write it again. Because that wasn't even a subgroup. So it's E, A, B, and AB. Okay. This is a subgroup of G. Now you agree with me, right? Okay. So by the Lagrange's theorem, what do we know? We know that the order of H divides, let me write in words, the order of the group. So this will be equivalent with what? Can you tell me what is the order of H?
4.
4. And the order of G will be? It's a group with 10 elements, so what is the order of G? What is it?
10.
10. Oh, I like some other people to say not just Jack. So 4 divides 10. Contradiction. That was a problem. It was slick a bit, but. So where did the contradiction come from? From the assumption that G is a billion. So G is not a billion. Is it clear? Was it tricky, Jack?
For this one, was it exactly 2 elements, or there just exists at least 2 elements?
There exist at least 2 elements.
Okay. Then could you just take the dihedral group on n vertices? On 5 vertices? Because that has 10 elements and it's not a billion, and it has 2 elements which do have.
Wait. Wait, that's an example of you mean, right? The dihedral group. Yeah.
Yeah.
It's not an yeah, exactly. Yeah, that's actually a good thing. Maybe you should to see how the problem looks like. If you come up with an example to see how the example fits into the problem, then it's actually even better. But it's just a direct application of Lagrange's theorem. So you just look at one subgroup, and in fact, this is how you solve these kind of problems. It's very these are very straightforward problems. Anyway, I'm going to give you another one, which is in another prototype of Lagrange's theorem, which says the following. This was a Putnam B2 in 1969. I wouldn't say it's trivial, but I don't want to say it's hard either. The problem has the following statement. So show that, it's pretty classical at this point, show that a finite group cannot be the union of two of its proper subgroups. So when you hear something about groups and subgroups and you want to think of some kind of order, you always think of Lagrange's theorem. Now, in the question, does the statement remain true if 2 is replaced by 3? Okay, think about this problem for a bit. I see Nadia's comment here. Which one does, if you replace by 3? Always when you have statements like this, show that for 2 or for this doesn't hold true. But what if we modify this? Does it still hold true? Or maybe it does, you know? So you have to come up with an example maybe. Let's see. So how would you approach this? And keep in mind that the group is finite. This is a very important piece of information. The group is finite. So Jack, do you have any ideas?
I'm thinking of trying to show it's not a subgroup of G.
Which one is not a subgroup?
That the union of 2 proper subgroups, a subgroup.
Yeah, that would be an idea. Yeah, I think I saw this solution. So anyway, now let's suppose that we have okay, let me just suppose that we have a group G let me just name everything here. Suppose that we have a group G, right? And two subgroups let's say A and B, right? Whatever, you can put H and K usually, but I just want to put them differently, right? Moreover, assume by contradiction that G is the union of this, of A and B, of these two subgroups, right? But let's keep in mind one thing. From Lagrange's theorem, we know that that the order of A and the order of B, both of them divide the order of G, right? That's what we know. But also keep in mind that so since we have that A union B is G, and moreover we have that the order of A plus the order of B is greater than the order of G, right? Let's say greater or equal, but it's even more than that. But also there is one thing. Every subgroup, and this is how the tricky part of the problem, every subgroup of G contains the identity element, right? All right. But since we know that subgroups are close with respect to the inverses, are closed with respect to inverses. Well, what do I mean by that? Well, I mean that for X in S, usually we must have that the inverse is also in S. That's what I mean, it's closed. So since subgroups are closed with respect to inverses, let me see. This is a very delicate. So I want to, because in this way, I would like to obtain a better inequality here. So that's why I would like to obtain, maybe I should put here, this is something like, because I would like to obtain something better. I would like to obtain that the order of A plus the order of B is greater or equal than the order of G plus 1. So I should think of this. So I know that the subgroups are close with respect to inverses, right? Okay, but, okay. In fact, let me write with that. But they are also closed right, with respect to multiplication. Right? So this means that so X times X inverse is the identity which is in S. So this implies what? Hence, we have this equality, the order of A plus the order of B is greater or equal than the order of G plus 1. Okay, so we have this inequality. At this point, we're in a very lucky situation because we can play around with it. For example, we can divide by, so again, by the Lagrange's theorem. So we know from Lagrange's theorem that, what do we know? We know that, let's say the order of A is something like the order of G. So we know that this divides, and let's say this is the order of G over M, and the order of B, this is the order of G over N, with M and N positive integers greater than 1. Right, so we know this from Lagrange's theorem. And now let's veer everything into this inequality here. Let's put everything together. So this implies that let's see. This implies that, so this would be the order of G times 1 over M plus 1 over N is greater or equal than the order of G plus 1, right? So this means what? This means, which gives us that, well, 1 over M plus 1 over N is strictly greater than 1. That's obvious. Otherwise, right? It must be the case. But this is a contradiction. Why is this a contradiction? Well, because keep in mind that these guys here, look at them here, are integers greater than 1. 1 over M plus 1 over N will never be greater than 1, so this is a contradiction. This will be in contradiction with this here. And that's it. So this is how we solve the first part. So we get the contradiction. So G is not the union of A and B. Anyway, I think the official solution was a bit different. But this is how I thought of doing it. Jack, do you have the same idea in mind, or?
Yeah, what I did was I proved a more general result that the union of A and B can't be a subgroup, so it can't be G.
It can't be G. Okay. Ah, okay. Yeah, exactly. Mm-hmm.
And that just followed from there would have to exist an element in A that's not in B, and an element in B that's not in A.
Not in A.
So they're products in the union, but then you can show that the product's not in either of the subgroups.
Exactly. I think that's the official solution. Anyway, yeah, but anyway, that's good. And now let's see what do you think the second part? Do you think it's true? Can G be the union of 3 subgroups? What do you think? If not, then you have to prove it. If you think it is, give me an example. So what do you think? So give me an example of a group G and 3 subgroups such that their union is G. What would be that group? It's a trick. This part is tricky. I agree. So what we should think of? Maybe, what do you think of, for example, Klein group? Does this ring a bell? So let's think of, it's a pretty standard example in any abstract algebra course. Let's think of Klein group. And when I say Klein group, I think, I don't know how you do, well, I haven't taught that abstract algebra 1, I taught abstract algebra 2. Do you denote it by K, usually?
V sub 4.
V sub 4, ooh, dang. All right, V sub 4, usually I denote it by K. But V sub 4, this is the Klein group, and it has the following presentation. These are the set of, well, elements. So basically it's the identity and other three elements, E, X, Y, and Z, right? But these have the following properties, right? You know that the product of any two is the third one, right? So X, Y, Z, so it has the following, X, Y, Z are elements of order 2. Right? Basically, X squared is the same as Y squared, is the same as Z squared, is the identity. And what other property does this group have? That the product of any two distinct elements is the third element, right? So the product, let me write it like this, of any two distinct elements is the third element. Okay. So this is how a Klein's group is defined. And now, can you exhibit 3 proper subgroups? So let me call this G. So that G is V4. So this is my group. Now, can you exhibit 3 subgroups, proper subgroups?
Would it be the one generated by X, the one generated by Y, and the one generated by Z?
Exactly. So we can take the subgroups. Let's just say, okay, we can write it in this way: EX, EY, and EZ. Right? So let's say this is A, this is B, and this is C. Right? And G can be expressed as the union of this. Does it make sense for everybody? Right? They're proper subgroups. As you can see, they're distinct, so there is no problem. So this is how you think of a Klein's group. And if you want to, okay, let me just say, well, the table for the how is it called? The Cayley table for the Klein group. Table for the Klein group. That you group is the following. And you can, let me, whatever operation we have here, dot, whatever, star, whatever you want to put it. So we have E, A, B, or okay, let me stick to X, Y, Z, X, Y, Z, X, y, z. I forgot about the e. Sorry about that. So let me, oops. So we have the following. Let's say here, this is e, x, y, z. E, this x, y, z. Okay. So this is the KD table. So here you will have e, x, y, z when you multiply them. So keep in mind, this is the product of any two distinct is the third element, and the square will give you the identity. All right. Now this will be x, e, x, y will be z, and the last one x, z will be y. Right, so this is the, now this will be y, yx will be z, e, x, right? And the last one will be z, y, x, and e. So that's the table, if you want to put it like this. So this is the table for the Klein group. Anyway, I'm not getting too much into, well, I still have 10 minutes, maybe I'll go a bit over time. I will invite you, those of you who haven't taken an abstract algebra, I will invite you to take it. It's pretty beautiful. Anyway, I taught when I first came to tech in the fall of 2 years ago, basically, I taught abstract algebra 2. Well, it's about Galois theory. Anyway, so these are the story, this is the story behind the group theory and stuff, but I want to mention one more thing. I want to do a very beautiful problem that, you know, how they say you save the best for last. That's what I'm going to do. But before that, I want to talk a bit about rings and fields. Usually, these kind of problems don't appear too much in the Putnam. I think I've seen 2 problems in the entire competition about rings and fields. So that's why I don't want to discuss too much about them. So what is a ring? So let's start with the ring. So what's the deal with these rings? Well, usually rings mimic in the abstract setting the properties of the set of integers or of the set of polynomials or matrices. And now this time a ring will be endowed with 2 operations, not just one. And let me denote this generically by plus and dot, right? So this is, in fact, this is how we, and the definition states the following. A ring R, like above, is a set endowed with 2 operations. Let's say the addition. So this is what we call the addition. And multiplication. This dot will be called the multiplication. Okay, such that the following properties hold true, such that R with the first operation with the plus, and if we look only at this, we will look this as a group, is an abelian group. So you know what an abelian group means. We have seen the properties. So it's a group that is commutative with identity element 0. So we'll denote by 0, right? And the multiplication satisfies the following associativity and distributivity properties. Ouch. And the multiplication satisfies the following properties. Okay, so these two properties that I mentioned are the following. The first one is the associativity. And this says the following: x, y, z is the same as x, y, z for all x, y, z in R, right? And the second one is distributivity, which says the following. Well, as you can imagine, it's the distributivity of the second operation with respect to the first one, which is x times x, y plus z is xy plus xz for all x, y, z in R in this ring. Or you can have something like this: x plus y, z is the same as xz plus yz for all x, y, z in R. Okay, so these are the two properties. And of course, a ring, the ring is called commutative. Oh my, commutative. If the multiplication is commutative. Is commutative. All right. Well, it's also useful to say that we can, the ring has an identity, is said to have an identity, let's say element. And when I say identity element, I mean 1 with respect to the second operation. So this one is in R. If x times 1 is the same as 1 times x and is x for all x in R. And an element is called invertible. Right? So an element, let's say x is called invertible if there exists x inverse in R such that x inverse is the same as x inverse x and is the identity. Okay, so this is what it means to be a ring. This is what it means for a ring to be commutative, and this is what it means for a ring to have an identity element or an invertible element. It's not guaranteed for a ring that the inverse exists, and this is where the field, the notion of field comes into play. And let me just directly say the definition, so because we don't have any time left. Okay, definitely I'll go over time. So a field is a commutative ring let's say R with plus and right, such that any non-zero element x in R is invertible. So if I have a commutative with any element being invertible, when I say invertible, let me just say it again, there exists x to the -1 in R such that x inverse is the same as x inverse x, which is the identity. So that's what it means. And the examples here, let me give you some quick examples. We usually you learn about fields in Foundations of Algebra 2. For example, we can have Q, R, C are fields. But, for example, the ring of integers is not a field. So Z is not a field. Right? And moreover, the second example I have in mind, the ring of integers modulo n, this is a field if and only if n is prime. So we call about the field of integers modulo a prime. All right, and then now let me put everything in a nutshell. There is this theorem, amazing theorem. Probably you're wondering what's going on with the commutativity in a field. Well, there's this theorem of Weatherboard. I think it's 903 or something like this. But anyway, any finite field is commutative. You learn this in the foundations too. So any finite field you have, it's commutative. All right, now let me give you a quick example of a problem. I think this was some Romanian Olympiad problem. It's a very beautiful problem. So problem number, I don't recall the number. What number is it? Problem 5, okay. So problem 5 states the following. So let K be a field of characteristic. So the characteristic of a field will be a prime number, P, which is 1 mod, or it depends on the field, it can be infinite, 1 mod 4. Prove that any non-zero element, any non-zero element, let's say element in K, can be written as the sum of 3 squares of non-zero elements as well. From K. Let me just give you the main idea. This is it's a hard problem, but let me give you an idea. You see, when you have this thing here, modular thing, right? You think of some kind of arithmetic. Do you remember something about what happens with when P is congruent with 1 mod 4? Do you remember something when we talked about Legendre symbol and quadratic reciprocity? What do we know about, for example, -1? Is -1 a quadratic residue mod P? Right? So that's what we have to prove. In other words, so -1, the main idea is a quadratic residue mod P, right? So this is a quadratic residue mod P. So now you prove that. First, we show that -1 is a square in K. And the way we do this is in the following. Remember when we proved that there was this number theory problem that we did, and yeah, I think we did it in the lecture, which said that if I have a prime, which is 1 mod 4, then this equation, this congruence x squared is -1 mod P has a solution, right? And the solution was actually P minus 1 over 2 factorial, right? Remember that? So that was the idea. So let P be 4m plus 1. And now we just mimic the same idea from there. So by Wilson's theorem, we know what? So we know that P divides P minus 1 factorial plus 1. Basically, it's just number theory. So, and now since we have this field of characteristic P, it follows that. So this means that P minus 1 factorial plus 1 is what? Is 0 in K. So, which is equivalent, which gives us, let's say, which will give us what? If we replace this, so it will be 4m factorial. So this means that 4m factorial is negative 1 in K. All right, great. But on the other hand, let's look at this, each element from this factorial. So we have 4m factorial. So we know that 4m factorial, 4m, let's look at 4m, is what? Is, sorry, negative 4m is 1 in K. What else? 2 will be what? Negative 4m minus 1. And we keep going. So you will have 2m will be negative 2m plus 1. And this happens in K, all these relations. And now if we multiply all of them, so multiplying all these, so if we multiply all these equalities, we will have the following. So let's see, what do we get? So we will get that negative 1. Okay, I'm just going to say it directly. So it will be negative 1 to the power 2m, right? Because we have a negative 1 on here, right? We have 2m times 4m squared. It's basically the same idea, 4m minus 1 squared. And we keep going all the way to 2m plus 1 squared. So as you can see, so negative 1 is a square in K. Great. And now let me just say the main idea on how to show that any element can be expressed as the sum of 3 squares, because we have to use this fact. Now we use the identities. Okay, so so now take any two elements. So consider, let's say elements A, B in case, right, non-zero elements that commute such that AB is the same as BA. So we know that since these two commute, we know that A plus B squared is the same as A squared plus 2AB plus B squared, right? And also that A minus B squared is the sum of A squared minus 2AB plus B squared. And now I'm going to leave this to you. Try to consider to play around with the elements. So consider B to be the inverse of 2. And try to play around. So you can write any element as A, for example, times A times 2 to the negative 1 plus A to the negative plus everything squared plus B to the times 2 to the negative 1 everything squared plus something else. And try to play around with this. And play around with this. Anyway. That is the main idea. It's a very beautiful problem. Unfortunately, I don't have time to finish it, but anyway, I think you can do it. All right, guys, I'm going to stop here since I don't want to be late for my other class. And I'll see you on Thursday. On Thursday, we're going to have a lecture, and we'll start linear algebra. All right, thank you.